Okay, great. So this is day 2. Today is Wednesday or Tuesday. Let me check the calendar. Okay, good. Today is Tuesday. So this is day 2 of this is day 2, week 3 of our journey together. So welcome everyone. One moment. So welcome everyone to the class. It's a few of us to start with, but hopefully the rest of them come right on board. All right, so yesterday we did rules of exponents 3, 4, and 5. Today, could you please head up with me? This is the 19th of July. (2022). And we are gonna finish up, hopefully, that's the goal. We're gonna finish up the rules of exponents today. At least that's what I have in mind. So hopefully we can do that today. Remember that as I am writing, please copy down the notes so that, excuse me, so that you can have a copy of your own notes and so that I can know that you're following along. So the topic is rules of exponents. We're continuing, and hopefully we can finish up what we started. All right. By way of review, anyone can remember the rules, the 3 rules we talked about it yesterday? Anyone can remember any one of them? And tell me how it works.
You said that you want us to tell you the last.
Any one of the last 3 that we did yesterday.
Okay. So when you have raised to the power raised to another power, you multiply the base. You multiply the powers. You keep the base and multiply it.
Okay. So what do we call that rule?
The product rule.
The product rule. Excellent. And then what's the next one that we looked at yesterday?
The quotient.
The quotient rule. Very good. Uh-huh. And how does that one work? How does the quotient rule work? You want to remember?
You have to subtract. You have to subtract the power.
Yeah. Yeah. Subtract the powers once you're dividing. Okay, good. And the last one that we did on yesterday was what? The last one.
The last one we did, what's the power rule? What I just said.
You say the power rule or the product? I thought you said the product rule.
The product rule. I have in my book the power rule. I don't know what I was writing, but
So
yeah.
the first one was the product rule. The second one was the quotient rule. And the third one was the power rule. Right? Because the power rule, let me go back to it. I hope that's the name of that probably might not be the name there. Let me check it. But it basically says that once you have 2 exponents, one on the inside, one on the outside, you could multiply them. What's the name that we gave to that? That was the power rule. Yeah, the power rule. All right, that was rule number 5 on yesterday. So we're gonna continue on rule number 6. All right, so rule number 6. And this one is an interesting rule, and it's worth noting, and we're going to talk about it right now. We already dealt with product rule, quotient rule, power rule. The next one is similar to the power rule, but it's another idea or another extension of the power rule. We call it the power of a product rule. And the reason is because if you look at it, if you look at the rule, it involves a product and it also involves the powers. Okay, so power of a product rule. So it basically says that if you have two terms, and this is going to help us to, I remember someone was asking, how can we actually, because there's one that we said, okay, not applicable, we can't use that rule for it. I don't know if Deja can remember that rule, that question. And she's like, well, how exactly do we do that question? And I said that we haven't gotten the rule to help us with that yet. Um, this this rule will be able to help us with that question. I hope I'm talking about the same question, but if I am, this is the rule that's going to help us with with that question that we left behind and didn't do. Excuse me. So basically, what the power of a product rule says is that if you have two terms, right, all raised to the power, right, all raised to an exponent, what you could do is that you can distribute the power across all the terms. All right. Um, that's basically what the power of a product rule says. So um, if we have terms, different terms, multiplied by each other, all raised to a power, the same power, right? We can distribute that power across the terms. Okay. And the thing is that the power of product rule both works both ways, right? So both sides are equal to each other. So let's say it in terms of words. So if we have terms, right? If we have terms, and now these terms could be the same or different. Okay. So if we have terms, it could be the same terms or different. Which are both multiplied by each other and raised to the same power, then we can distribute, or we could use the word carry, the power across all the terms. Interesting idea, right? So if we have terms, they could be the same terms or different terms, and we raise them all to the same, and sorry, they are multiplied by each other, right? And they're raised to the same power. We can distribute that power across all the terms. Okay, so That's what the power of the product rule says that we could do. Okay, so in general, we can write the given rule as follows. So we can write it as so let me make more space. So once you see it, hopefully it makes sense to you. So the idea is that we can take so that's let's go and find a exponent thing, and let's find a bracket. And so the idea here is that you have the terms a and b. Both of them are multiplied by each other, right? And all of them are raised to the same power, right, x. And so the rule says that if you have these terms, it could be a, b, c, or d, e, f, g, whatever. Once it's different terms inside the same bracket, and it's raised to the same exponent. What we could do is we can distribute this term across, this power, across all the terms. Alright? And so we have a to the power of x, and the same thing applies. It's going to be b to the power of x. Okay, so that's basically, the rule. So if we have, again, if we have terms which are multiplied by each other and are raised to the same power, we can take this power and distribute it or carry it across all terms. So we can say, you know what, this x is going to be for this b, and then this x is also going to be for a. Alright, so it's going to be a to the power of x along with b to the power of x. And that's essentially the idea with this particular rule. So let's consider some examples. So clear all drawings. Let's look at a few examples with this. So examples. So examples. Let me move that. So can you all hear me? Make sure I can be heard.
Yes, sir.
Okay. All right. So example number 1. Our favorite example. We like to use 2. 2 is, you can't get that simpler than 2, right? Let's use 1, but 1 is extremely trivial, right? I think a good thing that 2 provides, 2 is 2 is good because 2 is easy, at least at first. It gives us a good starting point. So we have 2 say times, let's say 3, and 2 times 3 all raised to the power of, say, 4. And so I guess Sierra, you could help me with what this answer is going to be. How can we write that?
Okay, that would be 2 to the power of 4 and 3 to the power of 4.
Excellent. So we could write it as 2 to the fourth power so we write it as 2 to the fourth power multiplied by, and we could use the multiplication symbol, or we can just use in brackets, right? 3 to the power of 4. Good, excellent. All right, so let's do something different. So we have a number multiplied by another number. They raised to the same power. We can distribute the power to each across each term. Okay, so let's say we have something different. So let's say instead of, numbers, we have, say, letters. So let's say we have H, or we could say NH, all raised to the power of 9. What's that gonna be, Rashawn? So not Rashawn, Deja. Deja's next on that.
N to the power of 9 times h to the power of 9.
Very good. So we have N to the power of 9 times H to the power of 9. Okay. And so that's how we would expand that or simplify it, or just say express it in a different way. Probably the best way to say it. Or one of the good ways to say it. So N to the power of 9, H to the power of 9. Right? So those are the natural extensions of the same question. But let's say we have, say, P, Q, and R, and we raise it to the power of, so we have P, Q, and R, we raise it to the power of 11. Sorry. So how would that work? What would the answer be for this one? This one is for Jasmine. How would we express this? Jasmine, though. Don't be shy. No, we can't have from Jasmine. Okay. Kaden, how would we have number 3? What would it be? We have PQR all raised to the power of 11. Can we have from you, Kaden?
I can do it.
All right, go ahead. Go ahead, Jasmine.
P11, Q11, and R11.
E11, Q11, and R11. Excellent. Very good. We just distributed across each one. So this is P to the power of 11, P to the power of 11, Q to the power of 11, and R to the power of 11. Good. All right, so let's see it done for numbers. So let's say we have, say, let's say we multiply that by 4. Let's say that this is 7, and let's say that this is 9, and let's say that, well, so that's let me do number 4 over. So number 4 is what we add now, we add 9 times what? 9 times, I think 7 times 4. So I think we add, let's say we have negative 6. Casey, what do we do? What would it be? It was for Casey. What would it be? Okay, I don't think our mic is working. So, Sierra, can you help us out with number 4?
Okay, it'll be 9 to the power of negative 6 times 7 to the power of negative 6 times 4 to the power of negative 6.
Excellent. Very good.
But isn't this a negative power? Shouldn't we put this over 1 or something?
We just applying one rule at a time. So obviously we can if we want to. I see a logic. Um, as you do rules of exponents, you realize that there's more than one way to skin the cat, right? So we can express things more than one way, right? And that's basically what these things saying, right? There's more than one way to express the same thing. And so we just want to apply this particular rule. So that's why we didn't put it over 1. Okay. So 9 to the power of negative 6. And as you begin to do math some more, it's just based on your preference, like which rule you would want to use. And sometimes using one rule is better than the other, and you realize that, hey, I don't want to use that route because that route is not the easiest way or whatever. But here we're just applying rule number 6 to these things. All right, just applying that and showing how it could be used. All right, so is there anything else we need to do? That's a good example. We showed it with numbers, we showed it with letters. Alright, I think we good. Alright, so alright. Alright, so yeah, I think that I wonder if we could try another example. We did NR, PQR, numbers, letters, negative number. That's good. Um this one is interesting. I want you, but this one is moving a little ahead, but this could happen. So say we have, you know, let's say we have um m to the power of 3, right? And so say we have h, not h is we use it. Let's say we have say q to the power of 5. And let's cover that and say, let's say all that is raised to the power of 4. Um, what's the way that we could do this?
I can't hear you.
Say it again.
I can't hear you.
Go ahead.
Um, M to the third power, M to the third power, to the fourth power, Q to the fifth power, to the fifth power, to the fourth power.
Excellent. Very good. Very good. So we're gonna say um, we're gonna say that this is going to be we need a double one in there, so we need another power. So essentially what we have is m to the third power all raised to the fourth power, sorry, and then we have the same thing for q, right? Q to the fifth power all raised to the fourth power. Now we learned yesterday how to deal with these two. So how would we simplify it further?
We multiply the two powers and keep the base. Oh,
Say it again.
never mind.
Never mind. Why you say never mind? What did we learn yesterday about when we have a power on the inside and a power on the outside? What could we do to them?
Yeah, I was saying we're supposed to multiply the powers. I think it's simplify.
Yeah, we could simplify, right? So we can multiply the powers. So it's going to be what? Help someone help me out. It's going to be what?
4 times 4? No.
4 times 4? No, no, no. No, not 4 times 4.
Maybe M to the power of 12 and Q to the power of 20.
Excellent. Because remember, we're gonna multiply these two powers, right? 3 times 4. So you're gonna have m to the power of 3 times 4. Okay. Multiplied by, say, q multiplied by q to the power of 5 times 4. And so we know that Miss Rashan Neely, what is 3 times 4? Rashan.
3 times 4 is 12.
What happened to your sister today, Rashan?
She went to work.
Okay. Okay. And then q, what is 5 times 4, Rashan?
20.
Excellent. So here we have the application of two rules at the same time, because we use the first rule, which is to take the power initially on the outside and to distribute it to the first term and then to the second term. And then after we did that, we used the power rule that we saw yesterday and multiply these two powers, right, to get m to the 12th and q to the 20th power. Okay, so
I have a question. So why we don't simplify the number 4 then?
why don't we simplify the number 4? Help me understand what you mean.
Yeah, because these are to negative powers and you're supposed to put 1 over them, right? And then you're supposed to find the power to be raised to, and then that would be simplifying it, right?
Why you say negative powers? Where the negative powers are?
Negative 6, 7 to the negative 6 power
Oh,
of
you mean
4.
for number 4, question 4.
Yes, sir.
Okay, so what's your suggestion for that again?
I mean, like how we simplified number 5. Shouldn't we simplify number 4?
Okay, propose to me how you would simplify number 4.
You did say when a number is raised to a negative power, you should put 1 over it to make it positive.
Mm-hmm.
So I think that's what we should do in this case, probably. I don't know.
Mm-hmm.
Or maybe we should multiply. I don't know. Yeah. Yeah.
You're
I think that's what we should do. But I'm
you're
sure.
right. You're right. You're right. It's just that I just didn't want to impose that second rule while we doing this. I just wanted to stick strictly to this particular rule. Okay. But this one, I did, even though it included a second rule, because I saw that it was a natural, something that flows right through. And so this one I made an exception for. Um, this one I made an exception for. Okay. All right. So Miss Albanique Bannerby, where's your sister? Where's Albanique? Hello, Miss Bannerby. I can't hear you. I can't hear you. I think your mic is not working. Oh, Altonique is right now. Okay, I was wondering where she was. All right. All right. So, okay.
But never mind, because that would be a very big number.
Yeah, it would be a very big number because you're raising it to the 6. Wow. Um, yeah, let's try another one similar to the first one, similar to number 5. So let's say, right, we have, um, let's say we have, let's say we have 3 to the second power times 5 to the third power times all times 3, all raised to the fourth power, let's say. And remember, this is multiplication in between here, so I'm going to indicate that clearly. Good. So, can someone help me out with number 6? How would we do that? What would we do? Anyone? Help me with number 6.
3 to the power of 2 times 5 to the power of 3. And then you gotta multiply them. You gotta multiply the power by 4.
Multiply the power by 4. Excellent. So, thank you, Miss Rashan. I really miss your voice because I haven't been hearing from you lately. You've been on strike, but I'm glad that you are here today. Um, in full force, so that's good. So we have 3 squared to the 4th power, and then we're gonna multiply that by 5 to the 3rd power, um, all raised to the 5th. Sorry, 5 to the 3rd power, all raised to the 4th. Good. So what did we do here? What we did is we took the 4 and we distributed it to 3 squared, and we took the 4 and we distributed it to the 5 to the 3rd power. Right? Essentially, we carried it to both terms. Okay, so we take the 4, we put it to 3 squared, we took the 4, we put it to 5 cubed, and that's where the 4 is. 4 is a part of 3 squared, and 4 is also a part of 5 cubed. Okay, and so now what we're going to do is we're going to multiply it now. So we're gonna multiply it now. So now what we have is going to be 3 to the power of 2 times 4. It's going to be 3 to the power of 2 times 4 multiplied by 5 to the power of 3 times 4. So we have 5 to the power of 3 times 4. So 3 to the power of 2 times 4 and 5 to the power of 3 times 4. And so if we were to expand that, or simplify it rather, 2 times 4 is 8, right? So it's going to be 3 to the power of 8. And Albernic, what is 5 times 4? Sorry, what is 3 times 4? What is 3 times 4, Albernic? Albernic, are you here? 3 times 4.
Oh, 3 times 4, sorry, that's 12. What is it? 8 times 12.
3 times 4, excellent.
Excuse me, I don't get it.
You don't get it? What don't you get?
I don't get how come they have like a 2 times 4 and then times 3 times 4 and then equal to 3 times 8 times 5 power of 4.
Okay, very good question. Okay, so make sure you come to class early, because if you don't come to class early, then you're gonna miss out. All right. So what we was talking about before you came to class was that we're looking at this new rule. Okay, so this new rule is on power of a product rule. Okay, and the new rule says that basically if we have some objects or some terms inside the brackets, right, and we have power on the outside, what we're going to do is we're going to take the power, multiply it. We can take the power and raise it to the first term. We're going to take the power and raise it to the second term. And so it's going to be a to the x times b to the x. So that's what that rule says. So we take the power and we distribute it to each particular term, right? So that means that if we have 2 times 3, all raised to the 4th power, it's going to be 2 to the 4th power times 3 to the 4th power. Just like how we have it there.
Yes, I get them one.
We get
I just don't get the bottom one.
Just don't get the bottom. Okay, I thought you lost from. I thought you didn't know the other ones either. Okay, good. All right, so that means it's easy then. So all we need to do is explain that one. So, well, with that one, sorry, that last one is not difficult. So the idea with that last one is the following. So if we look, we have, say, we have this, we have the 4, and we're going to apply it to the 3 squared, and we're going to apply it to the 5 cubed. And so that's why we have 3 squared to the 4th power and 5 cubed to the 4th power. Okay, good. Now remember, if we remember the rule from yesterday, if we have 1 power on the inside and 1 power on the outside, we multiply the powers. So 1 power on the inside, 1 power on the outside, we multiply the powers. So that means that we can have 3 to the power of 2 times 4, and that means that we're going to have 5 to the power of 3 times 4. Okay, 3 times 4 is 12, and 2 times 4 is definitely 8. All right, does that go down, Albany?
Yes, I get it now.
Okay, that's good. So with those examples, I think we're prepared to actually dive into our practice questions. So let's do them. Okay, so let's
Yes,
begin. Go ahead.
I wasn't had one more thing to write.
Okay, all right, so you need some time. Okay, no problem. I give you a few moments to finish write that down. All right, Bob.
Okay, then.
All right, so you finished copying that down?
Yes, sir.
Okay, that's good. So let's begin with the practice problems. I'm gonna switch over to the practice problems right now so that we can get actual practice on this particular rule. Rule number 6. Power of the product. All right, so let's get into it. So practice. So apply the power of a product rule. Apply the power of a product rule to each question. So apply the power of product rule to each question. And so let's say we have, very simply, we have, 3 times 4 all raised to the power of 5. And let's say we have, say, P R the power of 7 let's say we have 6 times 2 times 9 to the power of -3. And let's say we have A, B, C to the power of 4. Let's say we have pi squared times, or we can say pi squared P to the -2 or -3 and N to the power of 5 all raised to the power of 9. Let's say we have 16 times 7 y squared, and let's say this is 16 to the power of -4 all to the power of -5. And 7, let's say we have h so we have r to the power of 2n to the power of 3 q to the power of 5 all raised to the power of 4. Good. Alright, so those are the questions for the exercise practice. I'm going to give you 2 minutes to complete them. And let me get the timer ready. And the 2 minutes begins now. Almost done. All right, that's time. Okay, Albany, can you help me with number 1? What did you get for number 1?
For number one, I got 3 times the power of 4 and 4 to the power of 5.
You say 3 to the power of what?
3 to the power of 5
Uh-huh. Times.
times 4 to the power of 5.
Excellent. Times 4 to the power of 5. Excellent, because we distribute the 5 every time. Good stuff. All right. Altonic, can you help me with number 2?
I got P to the power of 11. I got P11, Q11, and R11.
Why 11? No, we have 7.
P11.
You
I
sure?
mean, wait.
You sure?
Oh, I read that wrong. I put 11.
Oh, you put 11. So we have 7 here. So what do you want to put? What is it gonna be?
Okay. P7
Uh-huh.
and R7.
7. Excellent. Good. All right. So Sierra, can you help me with number 3?
Okay, 6 to the power of -3 times 2 to the power of -3
Mm-hmm.
times 9 to the power of -3.
Excellent. And Deja, can you help me with number 4?
A to the power of 4 times B to the power of 4 times C to the power of 4.
Excellent. Boy. Jasmine, low. Can you help me with number 5? Jasmine, low. Jasmine, are you here? Okay, so I'm not hearing from Jasmine. Kaden, can you help me with number 5? All right, no, not hearing from Kaden. Casey, can you help me with number 5?
The meeting was reconnecting.
Say it again.
The meeting was
Okay. All right. So can you help me with number 5?
stop number.
Yes, number 5. All right, I'm not able to hear Miss Casey, so I'm gonna ask Rashan. Can you have me number 5, please?
Well, I could try.
You try. Okay, no problem.
Pi to the power 2.
Mm-hmm.
Um, P to the power -3.
So you don't want to put nothing on the pi, just pi squared.
No, I know what to do.
Okay, good. So you say p to the power 3.
And n to the power of 5.
Okay.
And then there's also a 9, so you have to multiply the powers by 9.
Multiply the powers by 9. Okay, excellent. So we're going to put 9 on each of them. Nice. So what is 9
9,
times 2?
9 times 2 is 18.
25. 19. Good. And what is -3 times 9?
-3 times 9.
Mm-hmm.
Um, I'm not even sure.
You're not sure. But what is 3 times 9?
27.
Okay, good. Just put a negative onto it.
I was gonna say that, but I was like,
Yeah. Because remember, a negative times a positive is a negative. So we have 5 times 9, which is
45.
excellent. This was a tough one. So I'm glad you were able to get it. All right, so we come right back full circle. I want Sierra to help me with this one.
Okay. Number 6. I got 16 to the power of -5
Mm-hmm.
times 7 to the power of 20
Very good. How did you get
times
that?
y, because I multiply -4 with -5.
Excellent. And a negative times a negative is a
Positive.
excellent.
And then times y to the power of -10.
Y to the power of -10 because 2 times -5 is
-10.
excellent. Very good. Very good. Wow. Well, impressing me now. 16 to the power of -5 times 7 to the power of 4 times 5 is 20. Y to the power of 2 times -5 is -10. Excellent. Excellent. Now, Jasmine, are you here? Jasmine Low.
Come here.
Okay, good. Can you have me number 7?
I could try, but I'm
Good try.
sure.
Okay, no problem. Still.
It's r to the second power to the fourth power,
Ah, excellent. Excellent. R to the second.
n to the third power to the fourth power, q to the fifth power to the fourth power.
Mm-hmm. Good. Very good. And so what do we do when we have the powers, 2 powers, one on the inside, one on the outside? What do we do?
We have the multiple.
Mm-hmm. Mm-hmm. Finish it. What are you gonna say?
Multiply the 4
Mm-hmm. So what is 2 times 4?
by the power I ain't do it all together yet. I just do that one in my head.
That's fine. What is 2 times 4?
8.
Excellent. And then n. What is 3 times 4?
12.
12. Excellent. And then 5 times 4?
20.
20. Very good. Very good. So there we have it. Any 10 out of 10s?
Me,
Name, say me. Oh,
Sierra.
Sierra. Okay, excellent. All right. Any other 10 out of 10s? Any 6 out of 6 out of. Oh, I
Those are all right.
say she said. It was one. I trust Sierra. She ain't gonna lie. I surprised Deja. She didn't get all right. Deja, did you get all right?
Yes, sir.
So I didn't answer my question.
I've unlocked the door.
Oh, yeah, done locked it up. Okay. All right. Okay, good. So, all right. So those are the answers to that. Power of a product rule. All right. And we had an application of 2 rules, especially in the last few. So let's do another rule, right? So we have power of a product rule, right? Do you think we're gonna have power of a quotient rule? Do you think that exists? Anyone? So we figure out what to do when we have on the inside 2 terms which are multiplied by each other, all raised to the power. Now we're gonna figure out what to do when we have 2 terms that are divided by each other but raised to the same power. Right? So that's the idea there. How do we, deal with such things? So let me take this one time and grab it. Keep. So now we're gonna look at power of a fraction rule. Okay, power of a fraction rule. So rule number 7. Now the rules does have an end. So just in case you're wondering, oh boy, what's gonna be the last rule? When are we gonna come to the last rule? There are only finite number of rules, so we come into an end soon. So we're not gonna be on this topic forever. But these are some nice rules for manipulation, right? Of numbers and letters. So good stuff. So rule number 7, power of a quotient rule, or power of a fraction rule. The rule basically says that if you have two terms, which are both divided by each other and all raised to the same power, you can distribute the power across both the numerator and denominator. Alright, so that's the power of a fraction rule. So in general, the given rule can be stated as follows. So we can write this rule in the following way. So it's a power of a fraction rule. So obviously we are expecting a fraction, okay, to show up.
Excuse me.
Go ahead.
Is this almost like the one we do yesterday, like when it was m and then we put a fraction and then like a r, so m fraction r? Is that like the one we had yesterday?
Similar. Remember the one we had yesterday? We subtract the powers.
No,
Uh-huh.
I mean the one where you had m and then you put a line and then you put r.
Yes. Yeah. It's similar. If we're dealing with a fraction. Okay, so let's actually do the rule or state it in general. Okay, so we need our fraction bar, but even before we have our fraction bar, we definitely need to put our power, because this is not just dealing with the fraction bar, but we're also looking at the power that's involved as well. So I get my bracket, we can need that. Now let us put it in a fraction. So let's say we have a over b all raised to, say, x is going to be equal to, anyone want to give it a guess? You think it's going to be?
ab to f, ab to the power of f.
AB.
Or like,
do you think? We have a over x all raised to the power of x. So what do you think it's going to be? Remember we said we can distribute the power across. What do you think? Alright, so let's try. It's going to be a to the power of x divided by b to the power of x. Alright, so that's our rule. What we do is we take the power and we distribute it across both terms, both the numerator and the denominator. That's how we tackle that. Alright, so let's try some examples. And for this example, I want Albany to help me with this example. So let's say, Albany, we have, say we have, let me raise this a little bit more higher so we can see it some, yeah, there we go. So let's say we have 2 over 17 all raised to the power of, say, 4. What's the answer going to be?
Okay, so that'll be 2 to the power of 4 and 17 to the power of 4.
Excellent. Excellent. So she said it's going to be, we can move that. She said it's going to be 2 to the power of 4 all over 17 to the power of 4, and that's absolutely correct. So 2 to the power of 4 all over 17 to the power of 4. So essentially we got rid of the brackets, right? If you look carefully, that's what we did. So it's going to be 17 to the power of 4.
I feel like this one is my favorite one so far.
You like that? Okay. Y is easy.
So once we have that, we're not supposed to go any further. We just leave it like that.
We are not simplifying all the way. I know you want to simplify all the way. We just getting exposure to the rules. Once we have all the rules, then we can start simplifying all the way. So if we were to try to simplify this all the way, we would actually change it from index form, right? And actually try to you know, write it in terms of standard form, and then see if we can find a common factor, highest common factor between the two, and then simplify it like that. If we were really trying to simplify it, we're just trying to write it. We're just trying to apply this rule for now. Okay, so we're not looking at complete simplification at the moment. Okay, Miss McKinsey.
Okay.
Because I know you want to simplify all the way. You want to get it down to its granular components. But we only applying the rule. That's it. Okay, so let's apply it if we have letters, say. So what happens if we have, say, if we have m over n all the way to the power of p. So Al20, can you help me out with this one? We have m over n to the power of p. What would that be?
Okay, so it could be MP and then a line and then MP.
Very good. Excellent. Excellent. So it's going to be, I like the enthusiasm and the power. It is exactly m to the p all over n to the p. All right, excellent. All right, good stuff. Okay. So let's say, for example, we have, say, so we deal with numbers, we deal with letters. So let's kind of mix it up. So let's say we have 27 over k to the power of f. So what would this be, Miss Sierra?
Okay, that'd be 27 to the power of f over k to the power of f.
Excellent. So it would be 27 to the power of f all over k to the power of f. All right, good stuff. What if I have, say, 3 to the power of n all over 9 to the power of n. I'll use 9. Let's say 7 to the power of n. What would this be, Deja?
We wouldn't have to do anything to it, right? Because it already has the same power. Both of them, the numerator and the denominator. So it'll be the same answer. I'm not sure.
You're not sure?
Wouldn't it be the same answer?
You sure you're not sure?
I mean, I'm not sure because it's not raised. Okay, I could see probably if you did raise it to a power, but it's not raised to. I mean, if you raised the entire fraction to another power, then I could have solved this. But it's not raised to anything. Both of them are raised to n, so I guess it remains the same.
You sure?
Or do you cancel n? I don't know.
Look at this carefully. So this is saying that we could take this side and transform it to this side, and this side and transform it to the next side.
So you want the opposite?
Mm-hmm.
So it'll be 3 over 7 to the power of n on the outside then.
Yes. Excellent. So that's going to be 3 3 over 7 to the power of n. All right. This is we give it to you in reverse. So sometimes you might have this, they give you this, and sometimes they give you the next. But you need to know that either way works. Either way works. Doesn't matter which way you put it. All right. So better than mine. Oh wow, it's 7:24. I really want us to finish these rules tonight, so I'm gonna skip on over to the practice questions. I notice only have 4 examples, but I don't want to have to continue with this on tomorrow. I want us to be able to combine everything on tomorrow, all the rules that we have. So we need to get through the rules today. So practice. So here we want to apply rule. What rule that is? Rule 7? Is that rule 7?
Yeah, so
All right.
Yeah, for the
So apply rule number 7. And so if we're applying it, it's going to be, so here we have fraction. So we have 9 over 23. And that's going to be raised to the power of, say, 2. What will be the result? Let's say I have 4 over 7 raised to the power of m. Would be my result. Let's say I have p over t. And you want to raise it to the power of 5. Let's say I have, say, say 14 over k to the power of -3. Let's say I have 2/7 to the power of, why should I say, 2/7, where this is pi and this is always the pi. And so the question is, how would we solve? Let's just do our last one, number 6. For good measure, let's say we have 9 m all over 10 p. I'm gonna raise that up to the power of n. Alright, so 6 questions. You have 2 minutes. To apply the rule 7. The timer has begun. Alright, that's time. Alright, so Rashan, can you help me with number 1?
That's 9 to the power of 2
Yes.
over 23 to the power of 2.
Okay, good. 23 to the power of 2. Good. Bernie, can you help me with number 2?
Okay, so mine was 4 to the power of m over 7 to the power of m.
Excellent. Jasmine Lowe, can you help me with number 3?
T to the power of 5. T to the power of 5.
Excellent. Sierra, can you help me number 4?
Okay, so 14 to the power of -3 over k to the power of -3.
Okay, power of Deja, help me with number 5.
2 over 7 to the power of pi.
2 over 7 to the power of pi. And also help me with number 6.
9m to the power of n over 10p to the power of n.
Say it again.
9m to the power of n over 10p to the power of n.
Okay, yeah. You want to break that down further?
Huh?
Huh?
You say if I want to break it down.
Yeah, and you could break it down further.
I think I know what you mean by that.
Help out.
I think you mean like you have to put m times n.
Very close. Exactly the same what we did previously. That'll be what? Someone help me out. Remember the same rule we used.
I'm kind of lost because m is not a power. So I'm lost. What do you mean?
Remember the rule we used? Remember this is the we have two numbers that are as a product, and we have a power. So what could we do with this power?
Oh, okay. We're
Yeah.
supposed to distribute the power. So I'm guessing that we add a 9 to the power of n times m to the power of n.
Yes. Very good.
And then, yeah, 10 to the power of n times p to the power of n.
Excellent.
I wasn't trying to go all that deep because you did say don't simplify.
Okay. All right. Good stuff. All right. So those are the answers. Any 6 out of 6? 5 out of 6?
Me.
Me.
All right.
Excuse me.
Yes, ma'am.
What if we got for number 6? What if we got the first part right, but we didn't do the second part of it?
That's fine. The second part is a little extended part. I didn't ask for that. I just put it because I only say apply rule 7. So that's fine. But I just was showing you that we can apply rule 6 as well to continue it. So this is a case where you could see where different rules could be used, you know. Different rules could be used, you know, based on the same question. All right, so let's try. I think this is our last rule. I think this is our last rule. I think this is our last rule. I don't have no fanfare. I don't have no hooray. This is our final rule for exponents. So once you know this rule, once you know all 8, you are an expert for exponents at your level. So you know all that you need to know in terms of as far as the rules are concerned. for exponents. We need no other rule. Now the trick comes in applying the rule and seeing the rule, you know, but once you know these, you are done with all the rules that you need to know. It's just now applying it, figuring out, hey, which rule that is. Is that two rules in one? Yeah, that's how it is be. So the final rule is the one that is very interesting. Sometimes it can sometimes it can slip our memory, or you know, but it's very useful rule. Very useful rule. We call it the fractional exponent rule. So rule number 8. The final rule for the night. We call it the fractional exponent rule. Fractional exponent rule. Fractional exponent. Okay, so now with this one, the idea is that if we have a term raised to the power of a fraction, we could actually convert that fraction into not the square root of a number or the square root of the term, but the root of the term. And that's an interesting notion. So if we have a fraction, right, a fractional exponent, so if we have a fraction as the power on top, right, so if we have a term and the number on top is a fraction, we could convert that term such that we have a radicand, such that we have a root and a power. Okay, so
So that's like fraction powers.
yeah, fraction powers. Yeah, so let's consider that one. So if we have a term raised to the power, or we say if we have a term whose power is a fraction, we can convert this term to some expression containing a radicand, a root, and a power. So what do we mean? So if we have, say, so in general, this rule can be stated as the following. So if we have, say, so if we have, let's say, we have a term, say a, and we raise it to the power of a fraction, and let's say the fraction is x over y, right? So we can write that. That's a to the power of x over y. So we can write that as some expression containing a radicand. And when we say radicand, what we mean is the same square root symbol, but it doesn't have to be square root, it could be any root. So this is the radicand right there. That funny looking symbol whenever you're doing the square root or cube root of a number. And the way you do it is that what ends up happening is that we still have the term, so we still have a. The top number, which is the numerator, becomes the power, so that's x, and the bottom number is the root, so that's y. Okay, so watch what happens there. The bottom number is the root, which is y, and the number at the top is the power.
Excuse me.
Yes, ma'am.
So how would we say that equation now?
How would we say it?
Yes, sir.
So we say a to the power of x over y equals the y root of a to the x. So let's say it. So if we were saying in words, we say a to the power of x over y equals equals the y root of a to the power of x. Okay, so a to the power of a over x equals the y root of a to the power of x. So if y is 2, it would be the square root. If y is 3, it would be the cube root. If y is 4, it would be the fourth root, right, of a to the power of x, whatever that is. So always remember, the root, or the denominator, is the root, and x is the power. Okay, so let's consider some examples of this. Hopefully we are not tricked by these examples. You gotta watch carefully. So we're gonna start off hopefully very similar. So if I want Albany to help me with this one. And vice versa. So if we have a radicand expression, we can turn it into a fractional exponent, a term with a fractional exponent. So let's say we have let's say I have a to the power of m over n. So tell me, Miss Albany, how can I write this?
Okay, so I would say to the power over m over n equals the n root of the power of m.
Very good. Very good. The nth root. Very good. Very good. You all learn quick. You all learn pretty quick. Wow. All right. I guess you're ready to do calculus. Right, Deja?
Pardon?
I guess you're ready to do calculus. How quick y'all learning.
We do that. That's a part of our curriculum over here. No, I just asked.
It's supposed to be your final. The last thing you learn is differentiation.
Wow.
Yeah. Supposed to have some.
Because I know my school don't offer like
You know, some schools offer AP maths and stuff. People
Yeah.
who really advanced, my school don't offer that.
Okay. Well, a lot of schools don't offer that stuff. Like telling you now. Most schools don't. Only a few schools do, you know. Because I mean, they barely haven't barely get covered of the BJC material. Judge covered, judge covering AP, right? So that's another thing. But AP really helps though. Um, AP really helps. If you have a school who does AP, that'll help you significantly to jump a lot of classes. Um, Even if you get a C in AP, you could skip a lot of classes. Um, you know, a lot of math
And
classes.
I know Queens College does it, but yeah, my school don't do that.
Yeah,
So I guess when I get there, I get there.
yeah. Hey, and I mean sometimes even the AP students admit to you that you know because it's so crammed, it's better for them just to do it in college because um, in college it's slower and you get to understand it better. Um, and so even though some people might skip the classes, they find I know a young lady, she did AP in school and she got a C, or something equivalent to that, and she skipped a lot of classes, but she still went and sat in the classes that she skipped because the AP that she did wasn't really, even though she got a C, she still wasn't strong in those areas. And so she still sat in those classes to get a stronger foundation. So, you know, so that then there's that. Um, but you do have to do a little bit of calculus at the end. You have to do how to take the derivative, and then you have to understand the notions of how does the tangent, how does the line the tangent line apply to derivatives. Um,
That sounded like Mandarin, but okay.
yeah, so it's not hard. It's really not hard. Once you get it, you know, it's not difficult. So yeah, so we used a here. What if I change the letter? So what if I say or before I even change the letter, let's stick with a because I know I don't wanna let's introduce this thing very slowly. So let's stick with a, but I want to say p over q. So let's see if we can do this. I want Al20 to help me with this one. So I have a to the power of p over q. What would that be?
Okay. So I got put the line.
Put the line. Okay, which line?
The line right there.
You mean this?
Yes, sir.
Okay, we call it the Radhakan. Okay, so she sent me put the Radhakan there. Okay, so we're gonna do with this Radhakan. What else I need?
And then put a Q underneath it.
AQ. You sure AQ or AP?
AP.
AP, excellent. AP. And then what happens to the Q?
You put it on top.
Put on
And
top.
not then right there.
Excellent. So this is the. Can someone read this? What does this say? If you were to read it.
That says um, P to the P to the A equals the P root of power of the power of A.
No, not quite.
Um, Q root a to the p power.
Yes. The Q root of a to the p power. Yes. The
You
Q
say Q?
the the q root of a to the p power. Okay, because this is the root.
Q or Q?
Q. The q root
Oh,
of a to the p power. Yes. Is that clear, Deja?
Yes, sir.
Okay. All right. So this one is for Sierra, who's been quiet all along. Let's see if she is understanding. Sierra. You know, for Sierra, we gotta make it difficult. So,
LOL.
all right. So let's say, let's keep it with A. And let's say we have 2 over 3 equals, what would that equal?
Okay, so we're gonna put the 3 outside the square root.
So we're gonna put the 3 outside the radical can. Okay.
And then a to the power of 2.
A to the power of 2.
Uh-huh.
Okay. A to the power of 2. So how would I read it? Mm-hmm.
I know how to read.
You don't know how to read it? You don't know how to read English?
Uh-uh.
I could try.
You don't know how to read English?
I just know how to do it.
I just put in your leg. It is the radical. Why I say radical? It's radical. This symbol is radical, not radical, not radical. Radical. The radical. The radical is the what's inside. Okay, someone said they want to read it. Go ahead, read it.
The cube root of a to the second power.
Excellent. The cube root of a to the second power. The cube root of a to the second power. Excellent. All right, so not every time you're gonna be lucky to get a, right? It doesn't even have to be a letter. It could just be pure numbers. So, but let's not do that first. Let's say we have a number, but one moment, please. All right, sorry about that. Okay, so all right, so let's continue with our discussion. So we want to say, so say we had say yeah, so say we had m over 4, so it's gonna be equal to, this is for Deja. How do we do this?
Is that M or N?
That's m, sorry.
M. Okay, so the fourth root, it'll be the fourth root of 2 to the M power.
So the fourth root of 2 to the m power. Excellent. Quarter of 2 to the m power. Very good. Okay. We can still manipulate this some more, and with this one I'm gonna ask Jasmine to help me. So we can look at it with just pure numbers. So say for example we have 9 to the power of 1/2. What would that equal to? What do you think? Yes.
Two root
2 root, okay.
9 to the first power.
9 to the power of 1, excellent. Now, she's right. But when we have the 2 root, we say square root, right? So if we have 2 root, yeah, that's fine. If we have 2 root, we say square root, and so that's what we call it. And every time we have the square root, we don't have to put the 2 in front. That's just because for square root, we don't put the 2 in front. So that means the symbol that we're going to use is actually this one without the 2, because if it doesn't have a 2 and if it doesn't have a number, we know it's 2. That's just the rule. It's like, that's just the rule. If it doesn't have a number in front, we just say it's square root. So that's why you never see the 2 in front, because the only thing that you've been doing is square root. Except for when you're doing cube root. But so we don't have to put the 2 here. We could just leave it as that. And this 1, we don't even have to put it there, because 9 to the power of 1 is still 9. And so this is still the square root of 9. Both of them are saying the same thing. This is the more technical way to write it, and this is the more simplified way. Now, what is the square root of 9? Anyone?
3.
3. Yes, because 3 times 3 is 9. So that one is a little interesting there, but if you have 9 to the half, you know that's the square root of 9. If you have 81 to the half, that's the square root of 81. Alright, so let's do our practice. I know we're running out of time, but
This is just the other way to do it.
say it again.
If the thing what you just trying to show us is the other way to do it.
The other way? What other way?
Like a different way to do it.
A different way? What different way?
Yeah.
You mean number 5?
Oh, so yes, so
I really trying to understand your question. Go ahead.
I mean like so you don't have to do the first one. And you could just do the other one, what you put, equals 9, equals 3, clear?
Oh, okay, okay. I see what you're saying. So yeah, so if it only this only works for if it's a half though. This one only works if it's a half. All right. In any other case, you can't use that. You have to do it the regular way. But only when you have a half, it's the square root.
Thank you, sir,
Yeah,
for making me understand.
no problem. So let's actually get into it. So practice. There's a lot of different ways we could test you on this rule. They could be very cruel with this rule, or very nice. Okay. So apply rule number we call it rule number. This is rule number 1, 2. This is the last rule number 8. Apply rule number 8. All right, so rule number 8. So if we have 3 to the power of 4 over 5, if we have h to the power of 7 over 9, if we have 36 to the power of a half, if we have 27 to the power of a third, if we have p to the power of m over n, if we have 9 to the power of 14 over 17. All right, let's do these 6. I'm gonna give you 2 minutes to do them, and then we'll do them together. All right, so the timer has begun. All right, that's time. I want Jasmine to help me with number 1. What do we do for number 1, Jasmine?
Who is door number 1?
5 square root.
Jasmine. So Jasmine said the 5, the 5th root
The 5th root.
of what?
3 to the 4th power.
3 to the 4th power. Excellent. Good. Rashan, can you help me with number 2? Rashan Neely. Or Casey. Either Rashan or Casey, go ahead. Oh, we can't hear you, Casey.
Number 2, I have
Uh-huh.
9 root,
9 root.
H7.
H to the power 7. Excellent. All right, Sierra, number 36.
Okay. Square root to the power of 36 to the power of 1, which equals 6.
Excellent. So we could write this as the square root of 36 to the power of 1, which we know we don't have to write the 2 because if it's the square root, we don't have to write 2 because that's implied. We know that. And then the square root of 36, well, 6 times 6 is 36. Deja, number 4.
I have the cube root of 27, but I just put 27 because it's the power of 1, so I just put 27.
Good.
And then the answer for that is 3.
Excellent. So the cube root of 27 to the power of 1, which is still the cube root of 27. Now, the cube roots is going to be which number? You can multiply it. So if we have 3 times 3 times 3, we get 27. So 3 times 3 times 3 is 27. So the cube root of 27 is 3. Okay, now, Albany, can you help me with number 5?
The n root. N root of p to the power of n.
Very good. The n root of p to the power of n. And Al20, can you help me with number 6?
So I got the n root.
Number 6.
I got the line. The line, right?
The
And
radical.
I put the 9 at the bottom. And I put the 14 right there.
Oh,
Right?
that's true. No, this looked like a 9. Or was I trying to make a 9? Oh, interesting. Okay, that's a 9. Okay.
I thought it was a 9.
That is a 9. Sorry, that is a 9. I don't know why I thought I put Q. Anyway, 9, yes.
And I put the 14 on top.
Yes, at the power.
And I put the 17 in the row to right there.
Side. The end there.
And then equal it.
That's good. Your answer is right there.
We'll do both of them.
Your answer is right there. So, yeah, so these are the answers. Any 6 out of 6, 5 out of 6, 1. Okay, so with that, that brings us to the end of math for this evening. Let me make sure I grab this. And not only that, not only brings us to the end of math, that brings us to the end of our rules. So now you know every last rule that you should know 4 exponents. And so you'll be able to do those exponents question, hopefully, with some confidence and understanding of what you're doing. I'm not going to do English tonight, so I'm just going to allow you to leave. So please send the math notes, and then we'll meet tomorrow at 6. We'll continue with putting all the rules together and see the questions applying all the rules, all 8 rules. That's interesting. And so that should be interesting and nice to see all 8 of the rules applied together. That would be nice to see that. And then tomorrow we have to do English tomorrow because we didn't do it today. But see you on tomorrow, God's spell, for day 3 at 6 p.m. And take care. Please, please, please send the math notes. Please, I can't over exaggerate that. All right, but have a good night.
Bye.
All right, good night.
Bye bye.
All right, take care.